To be able to better understand what Bohr did with light, and eventually to understand how an electron has a dual nature of being considered a wave and a particle, we're going to look a little bit at light. So we're going to look at light first as waves. How are light waves and what is a wave? Well, if you picture a wave, what I want you to picture are things like ocean waves, or a flag rippling in the breeze, or if you took a slinky and like went up and down with it. Okay, those are all examples of waves. A wave is just a repeating oscillation. Sometimes it's an oscillation of energy, sometimes it's an oscillation of matter, but it's just a repeating oscillation. As this slide says, a wave is a disturbance that emits energy. Okay, it's an oscillation. Light waves in themselves are also frequently known as electromagnetic radiation. You've potentially heard of electromagnetic radiation. I'll have a slide of it in a little bit, but what I want you to already be thinking about is the fact that you think of radiation as damaging, and not all radiation is damaging. So when we're looking at waves, what are we looking at? Number one thing we can measure about a wave is a wave's wavelength. A wavelength is the length it takes for the wave to repeat its oscillation. Meaning if you go from the top of the wave, as the picture shows on the right, to where it repeats itself at the top of the wave, that distance separating it would be its wavelength. That's measured in meters, nanometers, picometers, okay, small things usually because we're dealing with really tiny material. Frequency, on the other hand, is how long it takes, how many wavelengths. Frequency is a measure of how many waves pass a given point in any length of time. So to think about it, just the most easy. Frequency, on the other hand, is a study of how many waves pass a given point at a given interval of time. So, for example, it would be how many waves pass this point in a second. Is it 5 waves? Is it 10 waves? And by waves, we mean wavelength, from crest to next crest, potentially. The unit for that is hertz, shorthand Hz. What that is per second. So you're looking at how much stuff happens per second. It's 1 over seconds. That's what that S, the -1, means. Okay, it's a per second measurement. At the bottom right of the slide, it shows high frequency waves. And you can see they're very compact together. Because if you think about it, as that's moving, you're going to have more crests hit you in a shorter given time than the one below it, where the wave is very stretched out, meaning you're going to have less crests pass you in any given amount of time. Now, if you look at those pictures also and think about them as wavelengths instead, it's pretty easy to see how the first picture of the frequency shows that there are smaller wavelengths in high frequency, and the bottom picture shows there are bigger wavelengths in low frequency. If it's less frequent, you're going to have a much bigger wave. The electromagnetic spectrum is light. This is where visible light resides. Visible light is right here on our spectrum, which means it's like right here, up here. All visible light is again an oscillation of energy. It's an oscillation of energy that your eye records, but when we talk about other animals potentially seeing non-visible light, it just means that their eye detects things that exist outside of the visible spectrum. Okay? You are surrounded by electromagnetic waves all the time, right now. Okay? Your phone, the TV, they all receive radio waves. That's how they function. Okay? They're receiving a wave of energy moving at a frequency that corresponds to radio, a low frequency wave. The visible light your eye is receiving, okay, the ultraviolet light from the sun, you can't see, but obviously does damage to your cells. You've been to X-ray, you potentially have had an X-ray before, or at least understand how it works, that you can see images from that. Gamma rays are given off during a nuclear explosion. infrared, there's like infrared goggles and things like that, where you are actually seeing the electromagnetic waves that our body emits. We emit energy that moves at a frequency of infrared, and then there's microwaves that we use also to do things. So what I want you to understand here is that light is just one component of a larger spectrum. Okay? We receive to our eye waves that move in that region, but there are other waves all around you that you can't see. On that second slide, I showed the high frequency and low frequency waves and talked about how frequency, when it's like a high frequency wave, you have a smaller wavelength. This is an actual mathematical relationship. Wavelengths and frequencies are inversely proportional, meaning when you have big frequency, you have low wavelength because they're inversely related. And they are inversely related in such a way that if you multiply them together, you get the speed of light every time. The speed of light is 3.0 times 10 to the 8 meters per second. That is a number that you should memorize to be able to use in problem solving. We'll do problems with this equation, but essentially you need to memorize the equation and the number. Before Bohr was doing his experimentation with light and elements, other people were also studying light. And one of those people was Planck. What he was doing was looking at black body radiation, which is radiation coming from stars and planets. And what he was finding was the frequencies that were being emitted by those, okay, the lights and the colors that were coming off, had a relationship with the amount of energy being emitted or absorbed, the amount of radiation. And every time he looked at the frequency to energy relationship for any given wave, he found that there was a constant relationship. And that constant actually had a numeric value of 6.626 times 10 to the negative 34th. For any given frequency, the energy that it corresponded to, those two things had a relationship that was adjusted by 6.626 times 10 to the negative 34th. This is where the idea of quantum originated, with Planck. And the idea was light, which was just moving energy, right? Didn't have mass, doesn't have volume, isn't matter, is somehow producing energy and has enough energy to do stuff. Now, per frequency, every energy isn't possible, right? One frequency has one specific energy related to it, and that's essentially what a quantum is. A quantum is a discrete amount, a specific amount, a little packet of only that amount it can ever be received from that frequency. What we eventually started calling that little quantum or discrete amount of energy was a photon. And a photon is looked at like a particle. So it's weird because light is an electromagnetic wave. It's not a particle, but it can do stuff. It has energy. And so to study it with physics gave it a particle nature because it made more sense to apply it to the models that already exist. Okay, so a photon, when you hear about like a photon, it's just really looking at the light component, the energy component of light. It's not changing light, it's not giving it mass, it's just giving it a particle characteristic. Einstein took this idea of quantum further. He was studying light shining on a metal surface, and what he found was, depending on the frequency, electrons would be emitted from the metal or not. Okay? Not every light frequency would cause electrons to be ejected from the metal. So he said, okay, this particle nature of the photon evidently can be applied here too, right? The packet of energy of some wavelengths is not forceful enough to get particles to eject, electrons to eject, but then some are. Some are forceful enough to get it to eject. And classical physics couldn't do this because light was a wave. Okay, light was a wave, and basically any light then could do anything because it's just a wave. But if we start getting light particle characteristics where some particles are stronger than other particles, you get into the idea that the photoelectric effect is possible. So this is an image of what the photoelectric effect looks like. When you shine red light on the metal, nothing happened. When you shine green light on the metal, an electron was ejected when you shine even a more frequent or high energy wave on the metal, the electron was ejected even faster. Okay. So all of a sudden now with Planck and Einstein, our idea of electromagnetic waves has been adjusted to accept the idea that a light could be considered a particle or a wave, because depending on the situation, the math or the physical characteristics are viewed slightly differently. So now we get into Bohr, and Bohr doing experiments with the electron with light. The idea that the electron could also potentially have particle and wave-like characteristics was something that was better accepted and able to actually be applied.